Okay, so on page 34, these were just kind of a review of the different properties of the alpha, beta, and gamma particles. The one thing I wanted to point out that I didn't mention earlier was that the time you're exposed to radiation, ideally, if you want to be exposed to less radiation, you want to, what about the time? Do you want to increase the time or decrease the time? Decrease. So to decrease exposure, you want to decrease time. Another thing you can do to decrease the exposure is to increase the shielding. So if you decrease the time and you increase the shielding, that's the best way to decrease your exposure to radiation. So just kind of a review, like I mentioned. When you handle radiation, you want to be careful with it. But, radiation technicians, these are all very well monitored. And if you aren't monitored, then you need to find a new job. So, okay, polonium-208, it's one of the alpha emitters studied by Marie Curie. Write the equation for the decay, the alpha decay of polonium-208, and identify the element found. So, polonium is PO20884. Now, this is alpha decay, so you're going to have your arrow. And whether you put the alpha particle first or the alpha particle second doesn't matter. You're still going to get the same answer. So alpha 4/2. And then the mystery element here is 20482 pp. Hydrogen 3. Write the equation for the beta emission. Again, with beta emission, always be careful. So H31 arrow, beta, so it's going to be 3. And then what will the mass number be there? I mean, the atomic number be there? 2. So what's the element? Helium. Good. So lead-210, 82, another beta decay. So it's going to be 210, 83. And that's going to be bismuth. Bi. Fluorine 20, atomic number 9. So 20. What's my atomic number going to be? 10. So neon. So these decay equations have been pretty straightforward with these practice questions. Number 6 and number 7, there are a lot of words, and you kind of have to sift through. So if you weren't getting it right away, that's okay. You have to work for these. And, you can always rework these. So berkelium is an element with an atomic number of 97. Remember, Z is the atomic number. So it was first prepared at UC Berkeley in 1949. Berkelium was made by alpha bombardment of americium-241, which also yielded 2 neutrons. Write the equation for the preparation of berkelium. So this is how to make berkelium. It might get flipped around when you're trying to write this. So berkelium is B Decay, atomic number 97. Doesn't say what the mass number of berkelium is. But when it was made, it also yielded how many neutrons? 2. Good. So you can write out 1, 0, n 2 times. Or you can write it once and then write a big coefficient of 2 in front of it. I think when you're just beginning, writing out 2 neutrons is much easier to keep track of your math. So in order to make berkelium, americium was bombarded, americium-241 was bombarded with an alpha particle. What's the symbol for an alpha particle? 4, 2, alpha. So now I have mass numbers, atomic numbers. I'm missing the mass number for berkelium, but can I figure it out? Yes. So my sum of my mass numbers on the left, 241 plus 4 gives me 245. So on the right, I need to have 245 as well. 243. Good. And then just double check that your atomic numbers check out. 95 plus 2 gives you 97. 97 plus 0 gives you 97. So that was a challenging one.
You write them the other way, is it wrong?
As long as what is on the left and the right of the arrow is the same as mine.
Okay.
So you could have had your alpha particle first.
Your arrow doesn't change, it always goes.
Right. Your arrow always goes from left to right. Okay, and this next one, what's this?
So it's just your reactants on left, products on right.
Mm-hmm. And these are with the bombardment reactions. You're always going to have more than one thing coming together. So with your decay reactions, it's a little simpler because you just have one element decaying to something else, to 2 other things. So question 7, Californium-246 is formed by the bombardment of uranium-238 atom. If 4 neutrons are also formed, what atom is used for the bombardment? Okay, so Californium-246 is formed. So CF246, 98. And you can draw it. Write out your 4 neutrons.
Is that different than 2 produce?
It's the same. So just another way to say it. So 2 produce and is formed. Yeah. So I have my 4 neutrons. So uranium-238 is bombarded with something. We have to figure out that mystery atom. So the sum of my mass numbers on the right, 246 plus 1 plus, so 247 plus 1, 248, 249, 250, and then 98 for my atomic number sums. So 250 minus 238. Let's see. 250 minus 238 gives you 12. So that 12 is going to go here. And then 98 minus 92 gives you 6. So yes, you're right, Jake. That's carbon. So these will take a little bit of practice, but like I said, these last 2 were definitely harder. There's some practice problems in the pink book. Work through those. And the more you see these, I mean, if you think about it, you just learned all these particle symbols today, you know, so it's going to take you a little while to start using them. The last part of Unit 1 deals with radioactive decay. So given a half-life, calculate the amount of radioisotope remaining after one or more half-lives. So, if Susan and Dorothy make pies, let's say Susan makes an apple pie, Dorothy makes a rhubarb pie. Susan's pie is almost gone in 1 hour, and Dorothy's is gone in approximately 4 days. That tells you a lot about how popular they're popular, right? So let's examine the rate of consumption of these two pies. We have this pie, which is sounding good right now. So Susan's apple pie, after 15 minutes, only 4 pieces remained. Another 15 minutes elapse, and just 2 pieces remain. And then another 15 minutes elapse, and just 1. And then everybody's just taking little nibbles off that one. They don't want to own that whole piece of pie, right? So that's how Susan's apple pie was consumed. We look at Dorothy's rhubarb pie. One of my friends thought it was rebar pie.
That might be a little rough on your teeth.
No, not rebar. Rhubarb. I'm sure nobody would eat it if it were a rebar pie. All right, so this rhubarb pie, after 1 day, 4 pieces remain. Another day goes by, and 2 pieces remain. 1 more day, and just 1 piece remains. So my question to you now is, what is the amount of time required for half of the pies to disappear? Is it the same for the pies? Oh, it's different, right? So for the apple pie, the half-life, T1/2, the amount of time required for half the pie to disappear is 15 minutes. For the rhubarb pie, what's the half-life? 1 day. Excellent. So which is the better pie? Apple. So the rate of radioactive decay is expressed as half-lives. Just like pies, rates of decay vary from one isotope to another. Remember, we're talking about radioactive elements. These are unstable. So when you go buy a bucket of a radioactive chemical and it's shipped to you, it's not going to be that original amount that you purchased because it's going to be decaying. So a half-life is the amount of time required for half the sample to decay. So when it decays, it's no longer that radioactive element. Right? It goes to a new element and some emitted particle. So you will be presented with problems like this one here. Iodine 131 has a half-life of 8 days. If you start off with 1 gram of iodine 131, how much will be remaining in 24 days? So this, before we get started on this problem, you might hear of these radiopharmaceuticals. They have to have radioactive pharmacists on site to generate these radioactive labels, markers, or else by the time they get it shipped from UPS or FedEx, it wouldn't be in existence. It would be something else. So that's why a lot of times hospitals will have their own radioactive pharmacies. Okay, so now with this question, you kind of get an idea of what would happen in 24 days for iodine 131. I'm going to show you a very systematic way to set up these equations. Please follow it. I have set it up this way after watching years of students make mistakes. So whenever you approach a question like this, start out with time equals 0. So this is the point at which the question says you have 1 gram. So if you start off with 1 gram of iodine 131, how much will be remaining in 24 days? So just like the example that we did with the pies, we're just going to half and half and half. And there is an equation that you can very quickly answer, but I go through it this way with you so you can see. I don't really ever teach that equation because we always use full half-lives. We're not going to give you 1.5 half-lives or 2.5, 2 3/4. So after 1 half-life, which remember the half-life is 8 days, how much will remain of the sample? 0.5, yeah, watch your sig figs. So how many sig figs would you use? 3. You thought you could forget them? Now, what is the time when you have 0.5 grams? If it's a half-life, that's elapsed, it must be 8 days. So we're still not to 24 days. So we're going to have to go through another half-life. So half that. What's the time now? 16 days. And all I'm doing is dividing by 2. I divide 0.250 by 2 again, and but just to show you what I'm doing, if you had not so much of a straightforward number, 0.125, what would my time be? 24 days. So what happens to a lot of students, but hopefully won't happen to you, is that students, instead of starting off at t equals 0, they think, oh, I'm starting off at t equals 8. So this is 8 days where I start. And then they get 16, and then they get 24. So they don't ever get to this point. So that's why I always encourage you to write t equals 0. You're starting off at 0. Now, a couple of other things about this problem. It does not matter. Iodine 131, that's just telling you the isotope that's decaying. Cross out this number. I don't want you to take 131 and divide it by 2 and divide that by 2. You're looking for the quantity. Now this half-life, that's important. This is important, and this is important. But the 131, don't get trapped by thinking that's your starting quantity. So let's move on to technetium 99. So it has a half-life of 6 hours. If you start off with 32 milligrams, how much will be remaining after 24 hours? So write your t equals 0. What number can I cross off? What has no bearing on this problem whatsoever? 99. Don't worry about it. So if you start off with 32 milligrams, there you go. So you divide 32 by 2, and that gives you what? 16. What's the time? 6 hours. We've got to go through another half-life. So what's 16 divided by 2? 8. 8.0. Yes, very good. Not going to make that a mistake. Yes, good. And the time is going to be 12 hours. What is half of 8? 4.0. 18. And then, what's the time? 24 hours. So I would square this.
Is that the point that it's no longer, after that it's no longer effective, basically, or?
It would still keep decaying. So it's just, they're just trying to determine how much would be left after a particular time. So the decay, it kind of goes like this, where you have amount versus time. And so if you start off with 100%, you're going to kind of follow this curve eventually where you just have a little bit remaining. But you still, because you just still have a little bit left. So that's how this carbon-14 dating, you know, depending on how much carbon-14 there is, they can tell how old it is. So on the next page, were there any questions about this problem?
Just so with the bottom number with time, you're just each time you're writing the time down, basically you're just, since the top you're dividing it in half, you're taking whatever the time you're going to use the half-life, and you're adding that
Right.
to itself again.
Good questions. So if you think about this, each arrow is a half-life that you draw. So each arrow, so this is one half-life, 6 hours. Now, at this time point, you've gone through 2 half-lives, so that's
12.
2, yes. Oh, good question. On the next page, I have some more practice problems. And I'm going to give you these answers. You can work these. I just want to make sure we get through the last part. So the answer for number 1 is 12.50 grams. The answer for the second one is 94.0 grams. The answer for the third one, this is an atypical problem. You're working backwards. You probably will not see this, but it's a stretch. So kind of furthering your understanding of it. So if you want, you can start with your 5.0 grams and work backwards to get to the how much you originally had. Sorry, I didn't show you that. So if you start with the 5 grams, and then you work, instead of working from left to right, you work right to left. And you'll find that you start off with 160 grams.
So you're just adding 8.07
Mm-hmm.
all the way up to 40.
Right. So you're just doing the exact opposite of what we did. Okay, the last page of our Unit 1 note packet. The process of fission and fusion. Nuclear fission is the fragmenting of heavy nuclei. It results in a lot of energy. So it produces a lot of energy. What's going on here is a chain reaction. So you might have heard this chain reaction in movies, maybe even a new movie. But you have a neutron that's smashed into a heavy nucleus, like uranium-235, and then this heavy nucleus breaks apart into other nuclei. So it's kind of like this little neutron is a wrecking ball, and it's breaking apart this heavy nucleus. What happens, more neutrons are produced, which then react again with the uranium-235, and so this cycle keeps going. This is the type of reaction that goes on in power plants. So this is the example, power plants. It can get very hot. So that's why they have all these nuclear reactors that have to be cooled. Yes. So that's fission. I have an example of fission. And this is, it's kind of like your the nuclear bombardment reactions. What other isotope besides tellurium is produced by the nuclear fission using one initiating neutron of uranium-235? This is more of a stretch of these problems, more of an example. We will probably ask you more questions about how fission and fusion differ, that type of thing, as opposed to writing out fission and fusion reactions. So say that, I'll go ahead and write this out. 235, 92. and this is uranium. Sorry, I didn't write that there. It gives you tellurium, which is Te-137-52. What other isotope besides is produced? I have to also tell you, I didn't give you enough information in this problem. Another neutron is produced. So we have to figure out what the missing isotope is. So you're going to do, just like we have been doing with these nuclear reactions. It looks really complicated, but it's just addition and subtraction. So 235 plus 1 gives you 236. I need 236 over here. 236 minus 138. 8. Ninety-two is my sum here. So I need 92 minus 52 gives you 40. So looking at the periodic table, what element is that? Zirconium. So this is an example of fission, using that initiating neutron. Like I said, power plants use this.
And you said it was neutrons that are like wrecking or breaking down the nucleus.
So they have to be accelerated in some fashion to kind of make it break apart. Fusion is the joining together of light nuclei. This, like fission, produces a lot of energy. This is what goes on in the sun. Fusion is going on in the sun. So we're just going to make one nucleus, so 1 plus 2 gives you 3. 1 plus 1 gives you 2. So that gives you helium. So it's going to go on and on. What do you know about the sun? Very, very hot. So we're not going to be able to use fusion to produce energy because it's so hot. So you might hear about this cold fusion, and that's the topic of some movies. It's definitely a very interesting concept to have fusion going on at a very cold temperature. So it has not been achieved yet. So occurs in the sun, which is very